So yeah, it's nice to be back again. I want to talk to you about 6 impossible things. I thought it was a nice way to start Sunday. This is a talk that its earliest incarnation was during the pandemic, and I've done a couple of versions of this, but this is the one I've enjoyed putting together the most. It's the most complete, as it were, because I've got 2 hours. No, I won't use all the 2 hours. But it allows me to go a little bit further. And of course, because it is, I'll take some questions at the end, and obviously there's plenty of opportunity to discuss things during the conference. But I've already mentioned, but I'll mention again for those on the stream, my social media details. You can find me in most places. But what we're going to talk about is the quote, the title of this talk, 6 Impossible Things. It comes from a conversation between Alice, as in Alice in Wonderland, and the White Queen. This was in Lewis Carroll's Through the Looking Glass, which was published in the 1870s, 1871. And there is this wonderful quote where Alice basically says to the White Queen, "There's no use, there's no use trying. One can't believe impossible things." And the Red Queen responds, "Well, sometimes I've believed as many as 6 impossible things before breakfast. Now, I've caught you just after breakfast, but let's do 6 impossible things before lunch." Or alternatively, if you are watching this in a US time zone, hey, before breakfast. In fact, actually, let me just go back. I want to clarify one thing. These 6 things are impossible. Now, sometimes you need to kind of be very clear about the words you're using. When I say impossible, I mean not possible. Because I've gone on social media and asked various suggestions in the past. Okay, give me some things that are impossible in software development. Oh, and people come out with all kinds of great suggestions. A lot of them are very entertaining, but not all of them are impossible. Sometimes people say, oh yeah, delivering projects according to estimates. It's not impossible. It's a low probability event, but it's not 0. We are talking about a probability of 0. Okay, it's not going to happen. If we're saying things like, wow, that is so far beyond the reach of modern technology, it would take generations, maybe thousands of years to achieve this, then you've just told me it's not impossible. You've just told me the scope and the means of possibility. I mean, you won't be alive to see it, but that doesn't mean it's impossible. That just means, whoa, that's really hard. So do not confuse, oh, that's really hard for impossible. Okay? We are talking about things that, according to our current understanding of the way the universe works, and that could, of course, be incorrect, according to that, these are impossible. So I'm going to start off, we're going to do this as a countdown, which also, by the way, lets you know where we are in the talk. Yeah? And of course, I'm going to include a 0, but yeah. Representations can be infinite. Now, this is a thing that is impossible. Now, let's be very clear. Maybe this is entirely possible. It will annoy a couple of... oh, yes, I ought to say, this is a talk that will involve science, mostly physics, maths, philosophy, and code. So, perfect Sunday morning material. Importantly, I might annoy a couple of mathematicians. Anybody here got a maths background? Okay. I might annoy a couple of physicists. Anybody got a physics background? Yeah, okay. Yeah, by the way, everybody can include themselves in anything here, but I'm just picking on 2 groups to begin with. Everybody is a target, myself included, okay? So I'm going to make an observation here. There are no infinities in the physical universe. Infinity is a mathematical concept, not a physical one. Okay, whenever a physicist says, oh, and at this point you get an infinity, that's how physicists say we have no clue. Our theory breaks down. It doesn't mean there's an infinity. It means we don't have an answer. Yeah, so when they use infinity, it's shorthand for we haven't a clue. Okay? Computer scientists are particularly afraid of infinity, so they use softer words like unbounded. This sounds so much calmer and more gentle, but yeah, it means infinity. Or rather, we have no clue. Now, of course, you might say, well, wait a minute. Sure, I can get infinity on my computer. There, I can squeeze it. It's represented in my FPU. I can put it into 32 bits if I want to. I have bad news for you. That's not infinity. It's like the word infinity is not infinity. It's not an infinite number of things. It's a shorthand for, we can't look at that, we don't really know how to talk about it, but we can give it a name. Sure, we can name things that we cannot see and that cannot exist, or do not exist. I have a name for unicorns. It doesn't mean they exist. I'm sorry if I'm shaking your beliefs there, but they don't. We'll have to have a conversation about Father Christmas at some point as well. But the point there is I can have a name for it. Now, what's a useful source of the value infinity? Well, here's a useful source. Yeah, if you need an infinity, you can just get it just like that. Now, that is what IEEE 754 says. Mathematicians have a slightly stricter view. Division by zero is undefined for real numbers. Okay, now, it's the first point we're going to hear the word undefined today, but it won't be the last. In fact, that's true for the conference. It won't be the last time you hear this term. But let's be very precise. This is a mathematical definition. There is no undefined behavior in mathematics because there is no behavior. It just is or it isn't. It's right or it's wrong. Okay? If you have something that is undefined in mathematics, it means we can't do anything here. There is no behavior. We're done. Or you have an opportunity to create some new mathematics. That's what mathematicians love doing. If you find something undefined in physics, it's an opportunity for new physics. If you find something undefined in your C++ code, that is an opportunity to not go home when you thought you were going to go home. And if you work from home, I'm sorry, there is no escape at this point. You are trapped. You will never leave it. No, it's just, just another few minutes. I think I've got this one. So let's talk about numbers and this whole thing. I mean, obviously you know that representations can't be infinite. In fact, every single one of these, or pretty much all of these impossible things, you know if I state them directly. But it's the fact that what happens in code sneaks up on us indirectly and surprises us. So a number of years ago, I edited this book, 97 Things Every Programmer Should Know, sort of a crowdsourced and open source book. And there was this piece from Chuck Allison, who at the time he was editor of Better Software magazine. Prior to that, he was contributor and editor of a number of C++ journals. I've knew Chuck for a number of years. And he had, in fact, curiously enough, this is the only piece in the whole of the 97 Things book that I actually asked somebody for directly with a title. I asked people, please contribute, whatever you want. Random people from the internet, people I contacted directly. But Chuck was the only person I contacted directly. I would like you to write a piece on floating point numbers, because he'd written a really good piece on a series of pieces on IEEE 754. I'd like you to write, and I have a title for you, Chuck. Floating point numbers aren't real. Okay? And what do we know about floating point numbers? Well, I came across this one very recently, so thanks to Guy Davidson for mentioning this on the BSI standards reflector for C++. He mentioned this the other week, and I thought this is really interesting. Subtraction is functionally complete. To be precise, IEEE 754, floating point subtraction is functionally complete. That means you can construct any binary circuit using nothing but floating point subtraction. Holy crap. Okay, this is an article by Orson Peters just a few weeks ago, or a month ago. So this does not work if the numbers in your machine behave like the numbers that you were taught at school. But it turns out the numbers that you were taught at school are a kind of like an abstract fantasy from the perspective of C++. Okay? They bear almost no relationship. So, I mean, this is what you were taught at school. 0, nothing. Yeah? Please don't divide by it. You can multiply it, and it's an identity operation, or rather, it reduces everything to 0. Add, and it's an identity operation. This is fantastic. However, guess what? Welcome to the world of computers. We have a -0, which is actually slightly different. And if you subtract -0 from -0, now I know the quiz is tomorrow night, but let's start today. What do you get? -0 minus -0 Plus 0, well done. Excellent. And what happens when we subtract plus 0 from minus 0? Well, I have a mix of answers. Yeah, okay. And plus 0 minus minus 0? You're getting the idea of this. Excellent. And so plus 0 minus plus 0? Excellent. So that gives us this beautiful arrangement, which kind of reminds us of a truth table. In fact, this is the first truth table ever. This was invented by Ludwig Wittgenstein published in 1921. We'll be coming back to this work in a bit. So here's what we get. Now, let's convert this to binary. We get that. And actually what we've discovered is we've got an imply gate with inverted inputs. This is fantastic. So honestly, if you are bored with your work, you can recreate the whole of computing from the ground up just using IEEE 754 subtraction. Obviously, if you're bored, please don't do this in production code. Now, the point here is that floating point numbers aren't real. As Chuck observes, real numbers have infinite precision and are therefore continuous and non-lossy. Floating point numbers have limited precision, so they are finite and they resemble badly behaved integers. I love that phrase. Badly behaved. I mean, yeah, let's look at how badly behaved integers are already. So I'm known for kind of identifying and spotting failure screens. Here's one, blast from the past, 10 years ago. Visual Studio telling me that my license will expire. Well, that's a very suspicious number. And what I love is that if you are in software development, you immediately look at that and go, yeah, that's 2 to the 31 minus 1. Because, who wouldn't know that? The rest of the population is just like, that's a random big number. But it's not. It's very... This license will expire in... That's very curious. There's something going on. But what I love is that clearly something else is going on the inside because your license has gone stale. Oh no, I'm good for a very, very long time as far as I'm concerned. Beyond the likely lifetime of human civilization. So clearly this is a problem that happened in presentation logic rather than before. It turns out that we have a few problems with our numbers because we've just gone very big and, well, something's not quite right. So let's look at some of the consequences of this. So the lovely quote, FizzBuzz was invented to avoid the awkwardness of realizing nobody in the room can binary search an array. Now, I'm sure you can all binary search an array. You're a competent bunch of individuals, and even on a Sunday morning, you can do this. So let's look at this as a problem. So here is a binary search implementation, pre-STL, that I've dug out of a book. So early mid-1990s. There are a few things. Let's just reformat it a little bit. It's a little bit dense, so let's space it out a bit, tidy a few things up from a kind of like a spacing perspective, and also embrace C++ a little more. And so this is a binary search, and what it will do is it will return you the index of where a value is or where it would be if it were there. Now, why is this particular implementation interesting? Well, this particular implementation is based on an implementation by John Bentley from 1983. A piece called Writing Correct Programs. It was in Communications of the ACM. It was part of his Programming Perl series. So he pointed this one out. He wanted to show the full version and do a proof that this works. So he's kind of added in all of the various constraints, the assertions, the invariants that we are expecting at every single point. And he verifies this by proof. This works. One of the major benefits of program verification is it gives programmers a language in which they can express that understanding. And that is very much the kind of like the beginning of the era where there was a kind of a boom, well, or an attempted boom, 80s through the early 90s, where formal verification was very much, if any of you went through a computer science degree, probably pretty much until the late 90s or early 2000s, you would have been subjected to doing formal proofs in Z or VDM. And the idea is like, yeah, this is good, it can help you to... Now, there's a lot of valuable tools we can pick up, but there are some issues. First of all, never fool yourself that this is the whole picture. These techniques are only a small part of writing correct programs. Keeping the code simple is usually the key to correctness. Now, I'm going to be a little bit skeptical and say I'm talking to a bunch of C++ developers, so the keeping it simple, it's not going to happen, is it? However, I would like to impose on you that this is still a good idea. On the other hand, several professional programmers familiar with these techniques have related to me an experience that is too common in my own programming. When they construct a program, the hard parts work the first time while the bugs are in the easy parts. Oh, this has nothing to do with formal verification. This is the everyday life of a software developer. You are very familiar with this experience. You concentrate, oh, that bit's hard. That is where the eye of Mordor shines. Okay? You are there. You are focused on that. The armies of your intellect converge on the hard problem. Meanwhile, a couple of little hobbits sneak through and cause an unexpected divide by zero somewhere, or an off by one error. Now, there is a certain irony to this. Why is there a certain irony? Now, this is some Java code. This is some Java code that lived in the standard library, the JDK, up until 2006. What is relevant here is that this code was written by Joshua Block. Joshua Block was a student of John Bentley. This is John Bentley's algorithm. It has been realized in Java. It is actually the same. It's a variation of the same algorithm I just showed you before in C++. And this was in the standard library. And this all worked because it was based on an assumption. The problem is, around 2006, people started using very large arrays. And there is a small problem. Yes, a couple of you got that. Well done. I did say there'd be some science, so a bit of astronomy, a bit of radio astronomy there. Very large array for those of you who are struggling. That is the very large array. The problem here is this, because we have this ingrained at school. Okay? Yeah, if I want to find the midpoint of two numbers, it's the average of the two numbers. You just add them together, divide by 2. That's great. There's only one small problem. When those two numbers are really, really big, they run out of space because representations cannot be infinite. But we don't see that because normally you don't worry about this stuff. Nobody ever had to worry about arrays being 32-bit addressable until relatively recently because you simply had physical limits that prevented you from running off that. So we can do it by finding this, and this works. This is fine. So the point here is the assumption was here. The assumption in the proof was here. This is why he didn't spot the bug. The bug was always there. The code was wrong since 1983. Okay? That algorithm was broken from the moment it was conceived, which is kind of ironic because it was called writing correct programs. There is, by the way, if you're looking for a term for this, there is a term, Muffrey's Law. Muffrey's Law. If you write anything correcting or criticizing the quality of someone else's editing, proofing, spelling, grammar, or whatever, there will be some kind of editorial error in what you have written. Yeah, you could see this all over social media. It's like, I think you meant to spell it like this, and then you find that, or it's spelled like this and you use the wrong version of it's. Just the universe is sitting there going like, oh, here's an opportunity for fun. And of course, it is based on variation of Murphy's Law. So, the point here is assumptions. Let's go back to philosophy, epistemology, and the nature of knowledge. Assumptions are a very curious piece of knowledge, or a very curious kind of knowledge. You normally know your assumptions when they are contradicted. You discover that you believed something only when you discover that it's wrong. You discover it in the moment you say, oh, I assumed that. At that moment, somebody probably told you, there you are working with your colleagues, and they've just spotted something in your code. And you go, oh, that's not right. Oh, well, yeah, it's like this. And they say, no. This is not how it works. The standard says this, the database does that. The network never returns that error code. Oh, I had assumed that. At that moment, you discovered you had a piece of knowledge. You didn't know you had it. It was invisible. Had I asked you 5 minutes before, you would have had no assumptions. So assumptions are mostly discovered in retrospect, like stepping on Lego bricks in the dark, which is an experience that I recommend everybody try at least once, but only once, because then you know what it's like. But there is that point. Even if I tell you, by the way, in this darkened room where you can't see and you are barefoot, there are Lego bricks. You know you have assumptions, you just don't know where they are until you step on them. Okay? So let's talk about this one. So way back when, over 50 years back, structured programming, Uli Johan Dahl, Edgar Dijkstra, and Tony Hoare. Dijkstra made this observation. I've assumed perfect arithmetic. So by the way, this was published over 10 years before the Bentley bug. I have assumed perfect arithmetic, and in my experience, the validity of such proofs often gets questioned by people who argue that in practice, one never has perfect arithmetic at one's disposal. Admissible integer values usually have an absolute upper bound. Real numbers are only represented to a finite accuracy, etc. So what is the validity of such proofs? If one proves the correctness of a program assuming an idealized perfect world, one should not be amazed if something goes wrong when this ideal program gets executed by an imperfect implementation. In other words, where reality comes into contact with the abstract ideas of your code. So going back to this code, I'll leave it in its original form, we know that if we want to deal with this, we can actually focus on that problem. In C++20, I'd just use midpoint, because that's guaranteed to be right. That's it. That's the point of midpoint. Okay? And if we're doing that, then we might as well realize that the whole of the algorithm is intended to do exactly what lower range does. At this point, you can actually get rid of the original code. This is my favorite form of refactoring. It's just like, oh, wait a minute, you can do this. Oh, it's in the standard library. So there's a whole load of stuff like that. So yeah, we've got that. Now, other things. This ship has now been retired. It's the Yorktown. So this is a US Navy ship, and there was a problem. This ship was kind of stuck for about 48 hours. They'd upgraded their system from some variant of Unix to Windows. Data contained a 0 where it shouldn't have. The whole thing was taken down, okay? And when the software attempted to divide by 0, a buffer overrun occurred, crashing the entire network and causing the ship to lose control of its propulsion system. Oops. So there's a kind of an observation here. Clearly this is not actually directly an operating system thing, because divide by 0 in an application shouldn't have this. Yeah, but what if it's in a device driver? It gets a lot more exciting. That's where this stuff happens and gets a lot, you're executing in kernel mode. Yeah, it gets much more exciting. No, I'm not going to blame Windows for this one. However, I would like to note that the world is a very unsafe place. I'm sure we're all aware of that. And I just want to ensure that you know how unsafe it is that the Royal Navy in the UK runs Windows on its nuclear submarines. And they use a special variant, and it's called Windows for Submarines. I just want you to think about that one for a moment and just, yeah. Naming is really hard. Now, you might be thinking, well, hang on, Kevlin, you just told us that dividing by 0 gives us infinity. I did not exactly say that. I said floating point division by 0 gives you that. Integer division by 0, that's the emoji for undefined behavior, okay? It's just, so here is the problem. The problem that we are dealing with, as foretold by Shakespeare, who turns out was a great programmer, he wrote a whole play on memory management. It was called Hamlet. The most famous part of this one is to be or not to be. Is this pointer valid or not? I don't know. Have we deleted? Good question. Not really sure. There's a whole load of stuff that he carefully wove in. He tended to use a script programming language and favored the actor model. That's enough of that. But let's focus on what he actually said in Troilus and Cressida. This is the monstrosity in love, lady. That the will is infinite and the execution confined. That the desire is boundless and the act a slave to limit. We find a contradiction between what we want and also our imaginings and the reality of our platform. So let's talk about this one. Every question has an answer. To be more precise about this, I mean every question has an answer on the terms and in the frame that the question is asked. So here, a simple thing. Yellow, so when dealing with logic, we are very familiar that it's, typically we think of logic by default, we're talking about Boolean logic. We are talking about a two-valued logic. So here's the problem. Yellow is more happy than blue. Blue is more happy than red. Purple is less happy than yellow. Is purple more happy than red? Let's look at that one for a moment. And it's just like, in the frame of two-value Boolean logic, there is no answer to this. We simply don't have enough information. We can't conclude it. Now, some people would say, oh no, Kevlin, that's false because you can't prove it's true. Yeah, but you've just told me you've rigged the system. You've decided a new meaning for false. As opposed to, we don't know, you've decided. This is one of the classic problems with closed world logic systems, things like Prolog and many classic 1980s and early 90s attempts to reason automatically, is they use a closed world assumption. If I cannot prove it within this closed world, it must therefore be false, which is not at all how we think. So, to be precise, why am I showing it in this font rather than something else? Well, because I had a little conversation with ChatGPT. This was inspired by an article that I read. Based on the information you provided, we can establish the following happiness ranking. It does 1, 2, and 3 correctly. Yeah, yellow greater than blue, blue happier than red, purple less happy. Yeah. From this ranking, we can infer that purple is indeed more happy than red. What? No, we can't. And that is because you need to remember this. ChatGPT is your classic bullshitter. It is your classic bullshitter. It will offer you an answer with confidence. It is incredibly knowledgeable, but not very good at applying its being knowledgeable in practice, as it were. It will try and offer you a people-pleasing answer, but it is bullshitting, okay? It's just going to offer you kind of confidence. Do not confuse confidence for correctness. This is very useful when you're browsing social media and politics, okay? Now, here is the point. What happened is it pattern matched similar structures and said, oh, it must be like this, because you know what? There's a lot of stuff out there, a lot of material that kind of looks, this is this, that is that. Therefore, what is this? There's a lot of things. It kind of matches some of the stuff that's out there, and it kind of gives you an answer that's wrong. And the article I took this from was a piece written last month, Matthias Ramaker's Why ChatGPT Talks the Talk but Doesn't Walk the Walk. Humans remain unique in their ability to respond relationally. Relational frame theory proposed that human cognition and thus intelligence is founded on our ability for relational responding. In other words, responding to one event in terms of its relationship to another. So let's talk about events. Let's talk about things like time and our relationship with time and what that means for some of the questions that we ask and the answers that we can or cannot have. So this is one I've used before. It never gets old. I mean, it's timeless. I mean, literally, it is timeless. This was many years ago, so to tell you how far back it was before Facebook decided to start destroying elections. In referendums and things like that. So it's quite a while back. And there is one false statement here. I mean, given we're talking about truth and falsehood. Your feedback will be used to improve Facebook. No. I've been using it for a number of years since then. There is no evidence that this occurred. However, the thing that is of interest here is this. Wow. Thanks for taking the time to make a report. That's quite a lot of time. 1969. But 31st of December 1969 feels strangely suspicious. It's not an arbitrary number, again, for the rest of the population. It's just like, that's an arbitrary number for you, or an arbitrary date. No, you're going like, that's really, really close to the epoch. Okay, the POSIX standard, the time function shall return the value of time in seconds since the epoch. By the way, the C standard and therefore the C++ standard does not tell you this. It just says something. But most platforms follow the POSIX version. And we know when 0 is. You can find 0 time So using sweet nothing here, you can find 0 time quite easily. Just look around. This is quite a good one. Now, I've been told that this is not actually a bug. This is a feature. Intel were not, curiously, strangely enough, Intel were not releasing device driver updates on the internet in January 1970 for a variety of reasons. But they do this one because it is the beginning of time and therefore precedes all other possible things. This is the driver that you should install if nothing else happens, because there is nothing that happened before the 1st of January 1970. I'm not going to ask for a show of hands, but there are some of you here who, like me, were born before the beginning of time. And my current rate of progress, I mean, of course, it's difficult to predict the future. We'll come to that one in a bit. But I think it should also survive I should also survive the year 2038 problem, which will make me eternal. And therefore, a number of you here can think, yeah, I am immortal. I was born before the beginning of time, and I will live beyond the end of time. I offer you that today, okay? Now, initially, when I first saw this, I thought, to quote Anil Dash, the natural enemy of the programmer is the time zone. I thought, I see what's happened. Something got 0 initialized, and then it got shifted because I'm in the UK, and Facebook is in the States, so their servers are the US. So therefore, it got shifted west, which basically puts 1st of January 1970 into the end of 1969. That was my initial theory. And obviously, we do make these various mistakes. I had this one last year on the train from... we know that Britain has always had a very difficult relationship with basically every other country in the world, but let's focus just simply on the relationship to Brussels at the moment. And apparently, the National Rail online system, which was created some years after Eurostar connected London and Paris, still doesn't get the fact that there's a time zone difference. Still doesn't get this one right. So if you're holding dates and times without either converting to UTC or also holding time zone data, you are doing it wrong. It's as simple as that. By the way, if you are doing these things, it doesn't mean you're doing it right. You're doing it less wrong. There's one other thing you need to account for, is the fact that sometimes governments change time zones. That is not accounted for. But just the basics here. However, there is something else here. I was thinking you go back a few hours into 1969. But since then, I have come to believe that was not the problem, that there is actually a far simpler problem. I want to introduce a bit of negativity into your day. Not much negativity, just one. -1. Because all you need to do is go back 1 second from midnight, and you're in 1969. So what do we know about that? So here's a copy of the C99 standard. The value, time t minus 1, is returned if the calendar time is not available. Oh, it's not 1969. There is no time before 1969. This is a problem. On systems that use the negative range to extend backwards in time, you have a small problem. Is that the negative domain -1 represents 2 things. Hey, something went terribly wrong, or it's 1969. I mean, maybe you did something in 1969 that has left everything going terribly wrong. I'm not judging. The reason that nobody ever worried about this is the probability that you ever encounter this error is incredibly low. But it's not 0, is it? Because time is an operating system service. You have no guarantee that any operating system service will return with a correct value. You don't control the operating system. The operating system controls you. There are days that feels truer than others. But this is a point. It's a service. It is an external dependency. It is not guaranteed to work. It has no requirement to work. Time may genuinely not be available at that moment. And there are also other reasons. Sometimes you can have an uninitialized clock. On embedded systems, this is more likely. But the point is, even on regular systems, this is still a non-zero probability event. You need to think of time not as something that is all around us, but as a resource that you get, like a socket. Okay? In fact, I'm going to quote Anne Hathaway's character from Interstellar, Dr. Amelia Brand. She made the observation, we need to think of time as a resource. So when you write things when you think about it as testing, I mean, I know she was talking about something else, but I'm going to repurpose this and also make references to films, because this is one of my favorite films. So the point here is, when you are dealing with time in your code, it's an external dependency. You need to treat it like a file. You need to treat it like a connection. Okay? It's not just a value that happens to change. It's a resource. Okay, so let's bring things away from the nasty world of external dependencies into the world that we think we control. The world of algorithms, the joy of loops and code that runs without reference to anything external. What we're going to do is we're going to write something that's going to calculate the arithmetic mean. Now, if you want to throw some concepts in there, feel free to do that. However, I want the code to be readable, so I'm not. We're just going to find the mean, the average, of a bunch of numbers. And I'm going to write it like this. Okay? So, yeah, that kind of works. We accumulate from begin to end. We've divided by the distance from begin to end. That's great. So again, quiz moments, but this one's easy. We've got some values, 1, 2, 3, 4, 5, 6. Begin, end, great. And what we're going to do is we're going to take the mean of this. What value are we expecting? 3.5, excellent, awesome. You can feel good with yourself, right? I feel so good that I'm going to have some water. Now we're going to change the game a bit. End is the beginning. So this is an empty range. What are we expecting? So I've had a 0. There's a mumbling of different answers which seem to be an exploration of the IEEE 754 standard. Now, I've seen this one used. I attended a conference last year where this was given as a, quirks of JavaScript code. Okay? I mean, JavaScript is kind of like it's a highly improbable language. And that's how it feels to program it. So anything happens. But actually, this doesn't get blamed. This JavaScript doesn't get the blame for this one. It's because this is actually very well defined in IEEE 754 to be nan. It's defined to not be a number, which I think we're all satisfied with. It is not a number. But it's different from dividing anything else by 0. So we love a bit of consistency. But yeah, it turns out that dividing by 0 does not have, when we say dividing by 0 in IEEE 754 gives you plus inf, that's not right, because dividing 0 by 0 gives you something else. Now, of course, we're all familiar with nan. I mean, thank you, Lufthansa, for this one. Here's your JavaScript experience. Trying to parse nan, but it is not a number. Whoa. Yeah. You can see that this is what happens when some calculation further upstream generated something, got converted to a string, and so on. This is what we call stringly typed code. Okay, so let's do a little more explorations of nans, because nans are they're kind of interesting. So I'm going to have a set of values, which I should have probably fully qualified. Sorry about that. I knocked that one off, and I didn't mean to. I'm going to insert 0. I'm going to insert 42. I'm going to insert minus 273.15. Okay, that's cool. The size of this? No, I'm not even going to ask you. This one's easy. Okay. This one's interesting. What's the size now? It's not 4, it's 3. Because nan does not behave, it turns out that doubles don't actually respect all those ideas people spend talking about, is it strict weak ordering, is it? No, they're not. It turns out that nans are incredibly badly behaved. They do not compare equal to anything, even themselves. But is a nan less than something else is always false, and is something else less than nan is always false. So therefore, sets do their comparison based on less than ordering, and so therefore, once you've got something in your set, there's no way you can add a nan, even though it's actually a double. Okay, let's try something else. Let's put the nan in first. What's the size now? Correct. Once you put a nan in, it completely poisons the rest. Now, a lot of languages actually say, yeah, this is really bad. We want our sets and things like that to behave in a sensible way, and they define an ordering for nan. And sometimes what a language will do is they say, nan exists above all others, so it always compares greater, or nan exists below. So that doesn't change the less than or equal than, but it changed the specialized implementation. But C++ has not done this, so it leaves you with this kind of excitement. Okay, and in fact, we can do count of nan. That was, that's not undefined behavior. There it is. Okay, okay, that's 1. That's great. Yeah, so's that. Yeah. In fact, I don't even need that there. It turns out that because of that relationship, it's just like, oh, okay. In fact, to get a real sense of this, if you put a multiset in, there's 3 of those. So this is a point that nan is outside. It's the way that we answer, is one of the ways that we answer a question that does not have an answer, but the problem is it doesn't behave like the rest of the type. We are answering outside the frame. So even when we have a marker for it, it will surprise us. How much does it surprise us? Well, it surprised us enough in 2020. Driverless race car drives it straight into a wall. So if you're looking towards the driverless car revolution, just a little bit of caution here. During the initialization lap, something happened which apparently caused the steering control signal to go to nan, and subsequently the steering locked to the maximum value to the right. This is the concept. I mean, if it wasn't going to be the right, it was going to be the maximum value to the left. But the point is, or it could have just gone straight ahead. Either way, this is bad. Something failed. When I retweeted the article, when I retweeted the post I found this from, somebody said, oh my goodness, they're writing the code in the car with JavaScript. Because immediately people think, nans, it must be JavaScript. People are very disappointed or even more shocked to discover, oh no, the whole nan thing, that goes back to the 1980s. We did not have to wait for the 1990s for that one to happen. We blame this one on the 80s, okay? But the point there, no, it was MATLAB, if you're interested. It was not. But yes, cars do use JavaScript, just to make you feel less comfortable. Now, the point is that we often have this idea of something not being something being answered outside something, and this kind of classification. I was going through some photographs recently, some failure photographs, some failure screens, and I found this one. You can tell how far back this is. The resolution is terrible. This is like 2006, 2007. Phones these days have amazing... I took this at Paddington Station in London. Paddington's not there it is. Okay, and then you're looking at it, going, oh, that's been delayed. 11, delayed. Wow, yeah, it is delayed, because the next train is at 1828. I feel a reboot coming on in a moment. And then you're looking at Aachen. Wait a minute. How do you get to Aachen from Paddington? I mean, if you know anything about the stations in London, of course you can't get to Aachen from Paddington, because Paddington serves the west and Aachen is east. Yeah, that's not the only issue, of course. But then you realize it's not a train. This is actually what we call test data, and somehow somebody messed up the system, and Aachen is alphabetically the first main station in the whole of Europe. I mean, it's hard to beat 2 A's in a row, yeah? So, let's talk about other places where this idea of something not being has a problem. I'm sure, so have you had this experience? You go to something, and you have this momentary thing, and I get it when I use a lot of apps, most websites. There's this moment where apparently all your stuff is gone. Depending how fast, my heart just skips a beat. It's just like, wait a minute, all my stuff, whatever the stuff is, if it's orders, if it's money, if it's arranged meetings, it's appointments, it's whatever. For a moment, boom, there's nothing there. Okay, in some cases, only logged in members have access to this. But I am logged in, and I am a member. Boom, and then suddenly it's there. This is an uncomfortable feeling, but it's also a failure to understand what the nature of the question is. And there is a question. There's a question here about state. So John Carmack, games programmer extraordinaire, a large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may execute in. Let's understand the states. What we've got here, oh, somebody was taking a photograph. If you want the photograph of the, there we go, that's John Carmack picture, yeah. That was the universe, that was not me, that was the universe. There we go, okay. The universe is enjoying this. I think this is Jens's way of trying to make sure that the talk doesn't go on too long, but I haven't even hit like the first hour, so. The point here is the way that somebody's done it, and people are often not very good at articulating the basic state model. And I'm not saying you should draw diagrams all the time. What I'm saying is, do you have an understanding? Oh, the frequency is increasing. This is fantastic. What we have is there is a container of orders. When we create the object that we're going to display, the container naturally initializes to its empty state. And the first thing we do is display it. We say it's displayable. And now what we're going to do is we're going to go and load up. And then there's a period of time, because it turns out the loading is not instantaneous. And we get orders 3. And then we display that. And that's seen as a second display event. So the first display event is we created a display. What's the container have? Nothing. OK, that will display that. The second event is now we've got the results to display. This is not the correct way to write this code. It is the most popular way to write this code, but it is not the correct way to write this code. The correct way to think about this one is we are in a loading state. This is not displayable. That's why it's called loading. When you receive the data, we can do it. Come on, yes, it's loaded. There is a loaded event. At that moment, we have an answer. Up until that, 0 was not the correct answer. 1 was not the correct answer. -1 was definitely not the correct answer. Nan was kind of close. Neither of the infinities were acceptable. But 0 is wrong. So the idea is that this is an answer outside the frame of this. Now I'm just going to, are we getting a reboot? Do we have, no, everybody's run around there. So we'll just move on. Excitement of the blank screen is too much. Yeah, the frequency has kind of increased. And the duration has also increased, which is exciting. Yeah, that's exciting. Okay. Right, so the timing of please wait was good. Right, so that's the correct way to do this. The correct way to do this, the correct way to think about it is there is no answer to your orders. Your orders cannot be shown, they cannot be iterated, they cannot be enumerated, they cannot be counted. They do not exist. Non-existence, the absence of something, is very different to there are no things, okay? So this is, I would drink all of this very, very quickly. Oh, hang on, can I just borrow that bottle? Sorry, can I borrow this bottle? Sorry, this bottle has a really important property. It's empty. So this is an empty bottle. It has 0 content. It's listed as having 0.33 litres as maximum capacity. Okay? It currently has 0. This is not a bottle. Do you see the difference? There is a huge, huge difference, and yet a lot of code confuses these two. Okay? It's like confusing null with empty. Thank you. Doesn't make any difference up there, but nonetheless. So the point here is thinking about it in those terms. And an observation that Nicholas Nielsen makes, or will make in a moment, in 97 Things Every Programmer Should Know is, this one's got quite long. Are we rebooting? So what we'll do is we'll just go back to give you that sense of continuity and recap. For those of you who are watching on the stream, you're wondering what's going on. It's all craziness here, because guess what? This is the real world. And it doesn't matter what the software thinks, this is the real world. So to get the continuity, we've got there we go, thank you. The real world is still biting us. But I am happy to take any questions at this point if there are any.
Hello. One question.
Yes.
What's your experience? Are there some compilers that do better than others in terms of the behavior you scratch the surface onto? For example, is GCC better than Clang in these edge cases?
Yeah. The problem is, so some of these are not to do with the compiler. So first of all, a lot of these are to do with the way that we approach it. In other words, if we are talking about floating point numbers, that's going to be IEEE 754. If your compiler is not doing the weird stuff that I describe, then it's wrong. It's broken. So, you know, so in other words, this is specified weirdness. The fact that set, or rather stood less, still does not apply a total ordering to floating point numbers is problematic, because that makes it less useful. Okay? The point is, I would like to be able to represent all of the values, or to use all of the values that are representable in a double, even if they are non-finite. I would like them to behave as parts of that set. Just as I can order pointers, including with respect to null, nan is effectively the null of doubles. I have a total ordering that works for pointers. Why do I not have a total ordering, given that it's actually a specialized thing? I'm happy for the less than behavior to stay as it is, because that's actually required by IEEE 754. But the fact that stood less does not specialize, that's not a compiler issue, that's a standards issue. Division by zero typically is treated more as a platform issue. Okay, so what does Windows do versus what does Linux do is really the question there, rather than what does the compiler do. Where the compilers can make a difference is by offering you advice and warnings. And that one is definitely your mileage may vary in terms of what are the customizable warnings. Can I turn the warnings up to maximum? I don't have a real sense as to whether Clang gives me more feedback than GCC. In these cases, they're good at some things and different at others. But basically, the answer to some of these questions, without changing the core language or the underlying platforms, the best we can do is first of all, better warnings. But the other things, most of what I've shown you is blind spots in our awareness. And it's us, it's not the tools. We can't blame the tools. But I will talk about using the right tools later. Has that stayed? Now, I've had my back. So thank you very much for that question. I've had my back turned to this. Has this been up consistently?
Kind of, yes. Do we want to do another question from the online world while we're at it? Or you?
Yeah, if there's a question from the online world.
There is a question. If developer can't rely on operating system services, respect of time t example, what could be used instead? Operating system is often assumed as all-time working part in a system. I'm aware of certified OS, but what about system using other OS?
If you can't rely on the operating system, what can you rely on? Well, the standard answer to this is write your own operating system. This is what created Linux, and has created countless other operating systems. I think the problem is that I don't think there is an easy way around it, whether something is certified or whatever. What we want is well-defined failure behavior. Because you end up, that went, didn't it? You end up with another issue, which is one way of doing reliability is what was the last known value? In other words, caching. Yeah, there's a little bit of an issue with caching as well, which we'll come to. There is no easy answer to this one, but it is making people more aware. It's the idea that time t should have a more obvious return, and we can argue about whether that should be optional, expected, exceptional, whatever. But the idea is that it is not clear to everybody that this can fail, and that's not advertised. One more question? Yeah. Yes.
All right. I've been thinking about the binary search example for a bit now.
Yeah.
Because the overflow behavior in specific, and I've been thinking I'm just here to confirm my theory. Because we're using unsigned arithmetic with size t there, the overflow is forced to happen with the standard. But if it was an assigned integer since overflow is undefined, the compiler could catch that and optimize that away into the more solution where it adds up the difference, right?
The point is, unfortunately, in this one, it's more a case that it doesn't matter if it's signed or unsigned. You have a problem. Yeah. And that the compiler has to know an awful lot about the context that you're working in. And that would lead to a case where the compiler go, strictly speaking, I shouldn't, but this looks like you're doing the midpoint. This is like Clippy. Oh, it looks like you're taking the midpoint of these two values. Let me provide you with the correct one. And that means it's very sensitive to a very subtle implementation feature that could disappear in the next version, certainly wouldn't be portable. So I would be very cautious about that. So I'd like to acknowledge that actually it's a fundamental problem with any form of integer, signed or unsigned, yeah?
I just wanted to know if with the unsigned arithmetic it's forced to fail. That's the main thing. And with signed, it could maybe optimize it away. Or
the problem is unsigned is guaranteed to wrap around. That's the problem. So it's kind of almost back to front from what we wanted. Yeah. Okay, so this we'll rely on this one. Let's pick this one up. In most real-world situations, people's relaxed attitude to state is not an issue. We are very casual with our conversations and how we relate to the real world. But unfortunately, however, many programmers are quite vague about state too, and that is a problem. So let's pick up on that other problem. I'm sure people have come across Phil Carlton's observation that there are only two hard problems in computer science. Cache invalidation, which is, by the way, the problem of holding on to the last known good value of time. When does that become invalid? Because you're returning people an answer, even if it's wrong, you're giving them a non-error answer, but yeah, it could be stale. The data quality varies. And naming things. We'll come back to the first one later. Let's talk about naming things. So there is a problem. We have in the standard library, there is a header file called algorithm. Now, why is that? It's not correct. And we even talk about this as algorithms. I even talk about them as algorithms. But that's not really true, is it? I mean, it's not that it doesn't contain algorithms, but let's be very clear. What is an algorithm? So there's this wonderful book, Logicomics, so a graphic novel that really explores the kind of foundations of mathematics, mostly through the lens of Bertrand Russell's life, but it brings in a number of other key individuals, Frege and Gödel in particular. And there's one point where algorithm is defined. What is an algorithm? It is a methodical step-by-step procedure described in terms of totally unambiguous instructions which starts at a specified initial condition and eventually terminates with the desired outcome. Now, those of you who've looked at the standard, is that what you find in the algorithms library? That it tells you exactly what the algorithm is for everything? No, that's not what it contains. I mean, there are some that, so let's talk about find. If you look at find, by definition, the wording of find is linear search. There is no other way to do that satisfies the constraint reasonably. So in other words, it's implied that it's linear search. It's never stated. So it's called find, but it's linear search. Now, if we're talking linear search, then that immediately puts us in mind of, hey, binary search. Oh, there is something in the standard that's named after an algorithm. So that is an algorithm. It's one of the few algorithms in the algorithm header. But frustratingly, as anybody who first looks at binary search discovers, it's almost entirely useless because it just returns true or false. It's like, yes, and. This is really frustrating. It's utterly counterintuitive that probably what you want is lower range, whose name does not give you at all a clue as to what's going on. But this is a binary search. This is the binary search we explored earlier. But we can say that, yes, this is an algorithm, even though it's got a funny name. It is an algorithm. This is the classic binary search algorithm. But then we hit stuff like sort. The standard resolutely does not define sort. It gives a bunch of constraints. I mean, it could call it intro sort, because that's pretty much every implementation of STL these days, but it's not required to be. So this is an important thing. The one thing that the algorithm header is short of is algorithms. It's got a lot of operations that you might choose to look up in an algorithms book, but it doesn't tell you what the algorithms are. So it's a misnomer. I mean, poor old, you've got to feel sorry for the word algorithm. It's had a really hard life, not just the STL, misnaming it. Sorry, Alex Stepanov, mathematician, sorry. Not just misnaming it. He's correct in saying what you want to focus on is algorithms, but once you've abstracted the algorithm, you have to say, do I care about the algorithm or do I care about its effect? And once you are talking about its effect, you are not talking about an algorithm anymore, okay? You are saying there are multiple implementations that can satisfy this desired outcome, both in terms of cost and in terms of actual relationships to iterators and the like. So they are not, most of what you find is not technically algorithms. But also, recently, the word algorithm, apparently there's a whole bunch of systems out there that use large amounts of data and do an awful lot of linear algebra on them, a whole bunch of matrix operations, and they are called AI systems, apparently, even though there's an awful lot of artificial, but not a lot of intelligence. But people keep saying, oh, it's the algorithm. No, it's not the algorithms, it's the data. Honestly, the algorithms are really quite innocent. They're very unsurprising. If I showed you all the algorithms involved in machine learning, it would bore you to tears. It's not exciting. Oh, look, you're multiplying another thing by another thing, and then adding it to another thing, and then dividing it by a whole bunch of weights, and then doing... It really is not very exciting. The algorithm is really not the problem. It's the data. Yeah, people have data and algorithms, people have got distracted by the wrong thing. It's not the algorithm. So algorithm as a word has come in for a lot of hard time. But given that we're talking about algorithms, I want to talk about something that does not satisfy at all the standard. Permutation sort. Not safe for work. It has factorial time complexity, or OMG complexity. So I wrote a series of articles, a series of blog posts in the last couple of years about esoteric algorithms. They're quite fun because they're educational. They get you to understand various things. In essence, it's an unoptimized search through the permutations of the input values until it finds the one arrangement that is sorted. To give you a sense, in the worst case, if I have 10 items, it will take over 3 million shuffles. It literally just yep, not that one, yep, not that one. In fact, we might say, hey, if I'm doing this in C++, I mean, C++, I've implemented this in a variety of languages. Well done, C++, you take the least code. So it turns out that C++ is a great language because you can implement permutation sort in just a couple of lines. Okay? Yeah. Now, what we do is we can do it like this. We've already got stuff that does all the permutation work for us. This is fantastic. However, back to ChatGPT. I said I did one other version of this talk earlier this year, shorter version, slightly different emphasis, and it was in Amsterdam at Kotlin Conf. Now, I'm not a Kotlin programmer, and I said this to Hadi, who invited me along. He said, hey, we'd love you to do day 2 keynote for this. And I said, Hadi, I'm at best a Kotlin tourist. Okay, I'm not a Kotlin programmer. And he says, actually, we'd like something other than Kotlin, because day 1 keynote is all about Kotlin announcements, so maybe something a little bit more mind-bending. Okay. And I said, I've got some code in my talk, and I will translate it into Kotlin. That's fine. No, not a problem. And I'm looking, I think I'm going to do permutation sort in Kotlin. And I'm hunting around. My Google foo is failing me. I'm looking for a standard way to generate permutations. I've implemented this algorithm in C++, I've implemented it in Groovy, I've implemented it in Python, or it's easy in each case. Surely Kotlin, a language which people value for its simplicity and its directness and its commodity, I couldn't find it. And then somebody suggested, oh, you should go and look at ChatGPT. And there was a reason they suggested it. Yes, the Kotlin standard library provides a way to generate permutations of a list using the permutations function. Awesome. Here's an example of usage. Oh, okay, yeah, list.permutations, and then I can iterate for permutation in permutations. Oh, cool, nice. This will output, what? Hang on. This is your first sign that there is something wrong. But then he continues in great confidence. No, the permutations function requires a sequence of lists where each list represents a unique permutation of the original. Yeah. This means the permutations are generated lazily as needed rather than all at once. You know what? This is pretty good. So that means what I'm going to be doing is I'm going to be writing something like this. Okay? So I'm basically going to I'm writing this as an extension method, permutation sorted, and I'm going to go through the permutations of the thing. For permutation, but I need to have a termination condition if it's sorted. Okay? The only time you're ever going to exit it is if permutations is empty, hence you return yourself. Okay? That's the only thing there. Does the Kotlin standard library have a way to check if a list is sorted? Yes! Okay, it's sorted. Extension function. Now here's a point. It's an extension function, which basically means you get to kind of add it on after the class has been finished. It's very much like C# extension methods, if you're familiar with those. Here's an example of how you can use it. This time it does correctly give me Kotlin as the language. So therefore, I can go through this. If permutation is sorted, return permutation. Awesome, great, fantastic. This is all great. This is absolutely brilliant. I can write it in an even shorter form. Okay, I can make it more Kotlin-esque. This is fantastic. There's only one small problem with this. This is a complete trip. This is an absolute hallucination. Neither of these functions exist at all, anywhere. But what I love, and again, this is the pattern matching and the bullshitting. It replies with great confidence and great precision. Oh, look, here, I have an example for you. The interesting thing is, it actually gives answers that are, if they were in the Kotlin library, it would look like this. So that's the pattern matching. At least the pattern matching kind of works. It just can't tell the difference between what I'm thinking and what's real. Okay? We have whole specialisms in medicine for people to deal with that issue. Okay? This is a condition, unfortunately, some humans experience. But we regard it as something that we help people with. We don't weaponize it and put it out on the web. So it's interesting because it makes a number of statements. It says, oh yeah, these should be extension methods. Yes, they would be in Kotlin. That would be exactly the right way to do it. The naming, that is entirely correct. The use of lazy evaluation, so that you don't have to evaluate everything in advance, because it turns out there's a lot of permutations. Like I said, if you've got 10 items, that's over 3 million. You really would rather not use all of that memory all at once. Okay? You'd like to walk through them lazily. Deferred evaluation. So, in other words, in many senses, it sort of gets it right if it were, but it can't distinguish between the reality and that. So I kind of wrote my own is sorted, and then I wrote my own permutations, and I kind of got it to work. So yeah, you can do it. So thank you very much, ChatGPT, for telling me what it should look like, but that wasn't actually what I was after. I was kind of after something simpler. But there is a point here. It didn't have an answer. And rather than say, I don't have an answer, it bullshitted. It didn't know it didn't have an answer. Not every question has an answer. So surely there can be nothing worse than permutation sort. Surely. Yeah, hold my beer. So, the classic is BOGO sort. BOGO sort is, the job of BOGO sort is to just shuffle stuff randomly. Is it sorted yet? No. Keep on going. Guess what? C++ allows us to do this really easily as well. While it's not sorted, random shuffle. Now, there is a problem with this. In fact, there are two problems. I'm going to fix one of them immediately. The problem is, if it's already sorted, then we're not really using BOGO sort. The one time I actually used do while. Okay? I want it to be independent of its initial input. Excellent. Now this is true BOGO sort. What's the other problem? That's the next problem. That's the problem after the problem. Stood random shuffle. It was deprecated and then withdrawn. Technically, it's not there. I mean, it'll work on every single compiler that you're using, but technically it's not there. And the reasons are not, I'm going to say, the reasons are not good. The reasons are not sound. The reason that random shuffle, which is not random shuffle is not specified to use rand. Rand is not specified to be bad. There are lots of implementations of rand that are not good, and almost all implementations of random shuffle do indeed use rand. But none of this is specified. Implementers are free to change it so that it's better. And if somebody says backward compatibility, so what? That doesn't matter. And you know it doesn't matter because do you receive security updates to any of your devices? Yes, you do. all the time. And guess what? The purpose of a security update is to invalidate backward compatibility. We engage in breaking backward compatibility every single day, either as the receiving end or as the producers of the breakage. If we see that something is not good, then whatever is out there that depends on broken behavior does not deserve to be fixed. There's a lot of discussion. Sometimes people say, oh, yeah, but you might break an existing piece of code that does not deserve to work, is the bit that they're missing. The fact that it does not deserve to work is the reason that you withdraw it, because otherwise you have small things like, oh, security issues. So the fact that this was withdrawn, I think, is unreasonable, because it means that people no longer have easy access. So how do we solve this? I go and use a Mersenne twister. So now, as a user of the standard library, if I just wanted to mix things up a little bit, I now have to go into the random header. Now, the random header, there's a lot of good stuff in there. The entry level to random is like this. Every other language, oh, I just want random stuff. C++ does not cater for its audiences. There are 3 audiences for random numbers. 1, people who need to mix things up with a lot of control and a high degree of control, and to know this stuff. That's what this is for. Repeatable results that are statistically random. If you want to know the meaning of randomness, I suggest you go to Fran's talk tomorrow. No, Tuesday. When is it, Fran? Tuesday. Last day. Yeah, stick around. Rebook your flights. The other audience is the cryptographic world, where you absolutely don't want repeatability. Guess what? C++ caters to the first 2. It's the classic example of catering to the expert audience. And then there is everybody else, which is actually the largest audience of all. I often use Python, and I will just, sit there and go, oh, I need to just jumble this up so that it's not this, I don't care about all these other issues that people are doing. If you want to do a quiz for your kid's class and you want to randomize the questions, are you going to sit there and go, oh, I wonder if I should be using the Mersenne twister or not? No, you will not. The point there is the largest audience for random numbers is no longer catered for, which is frustrating. However, there is another issue here. I mean, John von Neumann made this observation. Anyone who considers that arithmetical methods of producing random numbers is, of course, in a state of sin. So we do find value in pseudo-random numbers, that repeatability. I often tell people, if you are using tests, if you have tests and you are using random data, please do not use true randomness. I want my test to be repeatable. Make sure that people know the seed so that they can repeat it. Okay? But we can do that if you want. I can tap into the entropy of my device. Now, I don't necessarily recommend doing it like this. This is slow and you will exhaust the underlying entropy. But when people say, here's an important observation, software cannot produce random numbers. But computers can. That's where we start remembering the physical world again. Yeah, there's a little bit of heat. There's a little bit of randomness and arbitrariness or non-determinism at the lower levels, which your operating system can quite freely tap into. You can read it off your chip. Most OSs will allow you to access that. So don't exhaust it. Just use it for the seed, and we're all good. Anyway, we now have we now have a BOGO sort that works. The question is, and this refers to the observation that was made, algorithm. The BOGO sort algorithm, but is it an algorithm? Hopcroft and Ullman in the late 1960s were very clear. A procedure which always terminates is called an algorithm. We're not actually guaranteed that BOGO sort will ever terminate. There is no guarantee. It's not like running through a fixed set of permutations. So we've got an interesting thing. Going back to this, and the famous quote, so if you wonder where it was from, Edgar Dijkstra, program testing can be used to show the presence of bugs, but never to show their absence. We're about to find out that this is the case. Because how do I test that my implementation of BOGO sort is correct if it's not guaranteed to terminate? So I can take some stuff, I can BOGO sort, actual begin, end, I can assert that it's sorted, as of now, I think it's called contract assert if I want to be correct, but honestly, until it's in the standard, it's not in the standard. So assert, and then I can assert that the result is a permutation of the original. Yeah, or I can make my life easier and just make it easy. I just say that the result is expected. Now, I will say that I have run this a number of times, and obviously every single time it's terminated because there's only 6 items, and randomly wandering through this, you are expecting termination. But let's consider this issue of what if it doesn't terminate? Then how do I deal with this? How do I assert that this will terminate by infinity? Well, this is a bit of a hack. So what I'm going to do is I'm going to assert false. I'm going to set an alarm for when. There we go. So if this alarm executes at infinity, then we failed. We didn't sort it. Yeah? I mean, that's a true statement. I can say it in English. I've just written it in code. There's a small problem with the execution. There's also actually another problem here. Infinity comes from the mass header and is effectively you end up with a cast, and infinity to unsigned, well, that's just garbage. Yeah. I mean, technically, here's undefined behavior. So what actually happens at this point? Well, if that's undefined behavior, then actually I can optimize that. And that means none of the code afterwards is necessary, and there's that. See, now that's the kind of refactoring I like. Okay? It's good optimization. Okay, what do we actually do in practice? We put in timeouts. We just choose, 1 second, that feels reasonable. And that's an important point. We've just fixed the halting problem. How's that for Sunday morning? But what have we actually done? The point is that the halting problem is phrased in terms of, can we determine whether or not, a priori, whether or not something will terminate in advance of its execution? And there are cases that we can. There are cases that we know will terminate, cases we know won't terminate, and then there's a bunch of others where we don't even know the answer. That's the problem there. But we can resolve this by adding timeouts, because what a timeout does is it says we will always have an answer. We introduce non-determinism. We will always have an answer. The answer is yes, no, couldn't tell in the time that we were given. Yeah? But you always get you're guaranteed termination, which is nice, but you now have to expand the way you answer your questions. Now, this relates to another point. Every truth can be established where it applies. We kind of already hinted that this is going to get kind of weird. Kurt Gödel, this is the English translation, and in 1931, basically said, yeah, there's some stuff that's not decidable. So Bertrand Russell and Alfred North Whitehead set out over a number of years to try and formalize mathematics in terms of something logical, and to try and show that it was complete and consistent. Principia Mathematica is notoriously unreadable and notoriously ignored, and notoriously referenced by many people, myself included, who have never even looked at the original text and never want to. But this young Austrian mathematician sat down and kind of worked through it, and kind of like, oh, it shattered the dream. It shattered a dream. This is the story of the early 20th century. By the end of the 19th century, everybody thought, oh yeah, we're almost finished with mathematics. Physics is almost done. We have answers for everything. And then along came quantum mechanics and Kurt Gödel. Boom! Any consistent axiomatic system, there will always be theorems that cannot be proven within the system. Okay, and in this classic Gödel, Escher, Bach, one of my favorite books, I've actually had to get a second copy because the first copy's fallen apart. And probably one of the best things I ever got out of a relationship with a particular girl when I was in my late teens. Her father was a mathematician, and he came up with all kinds of recommendations. So I was really there for hanging out with her father. All consistent axiomatic formulations of number theory include undecidable propositions. Okay, so do we have any examples of undecidable propositions? Yeah, sure. How long is a piece of string? Okay. What do I mean by that? Let's use Strelen. Okay, so we've got Strelen. I'll use the implementation that's I think it's given in KNR2. We start at 0, we iterate through while we're not null, and we increment, we return. Okay, there you go. Nice linear search algorithm. Not too hard for the morning. Under what circumstances does this work? Well. Yes, you see, that's the thing. The easy one is, there's 2 zeros that we're interested in. One is, oh, that should not be null, so 0. But that's not it. The other one is there should be a 0. Now, you'll notice that that's in gray, and it uses the existential and the universal quantifier because you can't write this in C. And it doesn't mean anything if you could, because what you're basically asking for, that there exists for an n such that it is indexable and it is valid, so therefore you cannot reference invalid memory. And although you might say, hang on, doesn't my operating system allow me to check if a pointer is valid? Yeah, not with the kind of results that we're after here. And also, that's outside the standard, even if that did do it reliably. The point here is that there is no way inside the system of Strelen in standard C that we can demonstrate that this will execute correctly or that it will even terminate. Well, the fact is that we know it will. The only way we can do this is by having a real machine with real memory and a real compiler with a real operating system. At that point, we interpret this. But we know that, but that's the point. Within the system of standard C, in the context of Strelen, we cannot demonstrate that this does the right thing. You can only demonstrate by looking at how it's called. You need the next larger context out, the next larger system out. So here we go ahead. This is well-defined behavior. Be excellent to each other. And Strelen of that, 26. Awesome. If I go ahead and do this, let's set up 5 characters. That's bogus. It's got no null termination. But guess what? C allows me to go ahead and actually use the literal quotes, deceiving you into thinking that there is, all of them were deceived. There was, in fact, not a null at the end. And when you execute it, hey, maybe you get that. Or maybe you fall off the edge of human knowledge into the precipice of what we often call undefined behavior. But there's no such thing as undefined behavior. Yeah, let's be very clear. Undefined behavior is not a thing. It's an absence of a thing. Because undefined behavior belongs in the standard. None of you work with the standard in your day-to-day code. You cannot code in the standard. That's not a thing. That's the point, is the standard describes something and then there is an implementation. Everything has an implementation. And so therefore something will happen, even if it's nothing. And this is my favorite one. This is a very easy way to get undefined behavior. Fantastic. Just don't initialize stuff. I mean, you'll get loads of warnings on a decent compiler, but it's, don't do this, don't do this. Yeah, but I'm going to let you do it. I'm just going to tell you shouldn't do it. Okay? I referred to Wittgenstein earlier on. This is the closing observation of the Tractatus. And that's the point. Something does actually happen at this point. So there is an interesting observation here that, particularly also when we come to think about machine learning, I'm going to refer to Adrian Collier's observation here. One premise of many models of fairness, how do we demonstrate that a machine learning algorithm is, or machine learning system is fair, is you can measure or prove the fairness of a machine learning model from within the system. That's what we're learning. Properties of the model itself, perhaps the data it is trained on. To show a machine learning model is fair, you need information outside the system. The importance of outside information is important. It's significant. I'm going to refer you back to 2020, here in Berlin. There was an artist, Simon Werkert, who undertook a rather interesting, the streets of Berlin are empty, it's lockdown. He got 99 second-hand Android phones and walked around the streets of Berlin with a handcart, causing traffic jams. Because you cannot prove things like this. You cannot prove. When somebody is saying, you get Google Maps telling you there is a traffic jam here. No, it doesn't know that. What it knows is there are a bunch of slow-moving Android phones. In many cases, that correlates with a traffic jam. Correlation is not causation, that classic reminder. And he just demonstrated that. People often talk about measuring engagement, but when I look it up in the dictionary tells me that engagement is a state of being engaged, or emotional involvement or commitment. I don't know that applications do that. They don't measure my emotions. I mean, if they did, they'd probably back away and go, okay, I'm really sorry here. That's what you measure. You don't measure engagement, you measure engagement. The observation here, you're measuring clicks and shares. We must be careful to not confuse data with the abstractions we use to analyze them. Really important. The answer that you seek is not necessarily to be found where it is. This relates to other things. Philosophical. The future is knowable before it happens. Again, another statement that you already know you don't know the future. Well, I hope. So I'm going to refer to Grace Hopper, who had this lovely observation. Programming is more than an important practical art. It is also a gigantic undertaking, the foundations of knowledge. So let us classify the way that we know things. I'm going to use a scheme set out by Philip Armour, the 5 orders of ignorance. He wrote this up in 2000. Sensibly enough, he started at 0. The 5 orders of ignorance. 0, a lack of ignorance. You know that you know something. I know that I speak English. Lack of knowledge. You know that you don't know something. I know that I don't speak German. Well, I mean, I have Speisekarten Deutsch, but that's it, okay? I know that I don't speak German. It is not a surprise to me that I don't speak German and cannot follow a full conversation. On the other hand, if you talk about C++ in your conversation, then curiously enough, I can follow half the words, at least. Lack of awareness. You don't know that you don't know something. Oh, that gets much more interesting. You don't know how to find out that you don't know something. Lack of process. You don't know the 5 orders of ignorance. Well, now you do, so we can get rid of that one. Now, we can reduce this to a much simpler schema. The known knowns, the known unknowns, the unknown unknowns, and the unknowable unknowns. Sometimes people say, oh, but Kevlin, you missed out the unknown knowns. What they mean is assumptions. That's actually unknown unknowns. You thought you knew something, but guess what? You were wrong. Yeah, that's already catered for in this model. But the one I'm interested in here is unknowable unknowns, the way that you cannot determine in advance the outcome of something. The halting problem is a classic example. In advance, given all the information, you can't work it out. You have to change the game, such as adding a non-deterministic possibility. This involves mostly the future. This was a lovely observation a couple of years ago. Great advice. I keep hearing, you got to future-proof your code. Okay, when naming things like tables, always future-proof. If you sell wine, calling a table wines will be confusing when you expand to beer. Beverages will be confusing when you sell ice. Products will confuse when you expand to services. So recommend they be called stuff or table 1. Yeah, you thought I was going somewhere serious with this. No. I worked with a developer and we were doing a code review. This was years ago. We were doing a code review. I was going through, this is good. And then my eye caught the title bar. Paul, you can't call this file stuff.cpp. He said, yeah, sure I can. I mean, he said, it's not wrong, is it? Well, true, it does contain stuff. But just because it's not wrong does not mean it's right, okay? So let's talk about the hardware side of things. When we try and predict the future, we do it at multiple levels. So there is branch prediction, which leads to speculative execution. What is the cost of a branch? Okay, well, this is the interesting thing. It's down to how well your CPU will predict stuff. Okay, there is pretty much an order of magnitude difference between a correct prediction and a failed prediction. If the branch is always or never taken, you pay almost nothing except checking the condition. Okay, what happens is the hardware fills up the pipeline with the instructions, and guess what? It goes there, and it's all good. The condition was correctly foretold. Okay, it was true, it was false. We branched to the right place. We anticipated. We have loaded in advance. Awesome. But if you don't have any guarantees or any other indications, then it becomes much more arbitrary. If it's a pure 50-50 token cost, you have to suffer a control hazard and discard the pipeline, taking another 15 to 20 cycles to build it up again. So you're talking about the cost of 1 to 2 cycles versus 15 to 20. So in other words, getting it wrong does actually cost. Okay, so there's an idea here. We're trying to predict the future, but there is a cost for not being able to predict the future. Normally that averages out. But of course, sometimes it does surprise people. If you remember Meltdown and Spectre. I love the fact that these two security issues got their own. They didn't just get a name. Most violations get some kind of name, but these actually got their own logos. I think that's so cool. But it also introduced the world of JavaScript programmers to low-level programming. JavaScript. I had this observation to make many years ago, before that, JavaScript developers criticizing C for being low-level and idiosyncratic, either have a very well-developed sense of irony or none at all. It suddenly meant, given that this was manifesting, these speculative execution issues were manifesting themselves at the JavaScript level. It's like, here's a language that knows nothing of its machine and yet is being exposed to behaviors that arise from that, and it has no way of talking about it because it's not in the system of JavaScript. But it applies at the low level. It also applies at the high level. People often talk about product roadmaps. It's a very tired metaphor, but I think it's a really valuable metaphor, potentially. If you're trying to say, here is where our architecture is going, here's where our releases are headed, this is what we're going to be doing over the next year, the next 2 years. I think a roadmap is a powerful way of thinking. And I used to say this a lot in workshops, and then everybody got stuck at home in 2020. So you have more time to spend online. I thought, roadmap. I bet there's a bunch of templates out there. So Google, PowerPoint templates for roadmaps. Oh my goodness, there are loads. And half of them look something like this. They show you a road. Fantastic. That makes the metaphor real. They show you a road, they show it winding. And the idea is you fill out your bits. And so now you can have a really cool presentation to impress your colleagues and your upper management. Here is our product roadmap. And that's great, except there's one small thing about this metaphor. There's only one road. Here's a map of center of Berlin. You will notice that it has lots of roads. That is the value of a roadmap. The whole point of a roadmap is that it has options. It has possibilities. If there's only one road, trust me, you don't need a map. Where are you going? Down the road. There we go. We've answered it. Yeah, years ago, my wife and I stayed on a Scottish island. And I'd sit in the morning. It's like, okay, where are we going to go stay? Well, where are we going to look with the kids? You know, the cottage we were staying at. And she'd see me online just like, what are you doing? Oh, I'm just using the map to figure out where we're going to go. She said, Kevlin, there is one road. It goes around the island. Your choice is you go left or you go right. That's your choices, okay? You don't really need a roadmap for that. And she was right. So the point is, so you see, I think a roadmap would be valuable. It's just that people don't know how to draw roadmaps. The whole point of a roadmap is it shows options. Here's where we will probably be in 6 months. This is our preferred route. But there's a couple of other possibilities. You show possibilities. That's what makes driving with these things actually useful. Hey, here's the kind of route we started with, but here's another route. It's 10 minutes slower, but it's more scenic. Or, oh, this route's now become blocked. This other route is 5 minutes faster. You respond to the situation. Real development is about acknowledging discovery. It's not about committing to a path that you said, oh, this is wrong. We now know it's wrong, but guess what? We're going to do it anyway. Okay? We have a plan, so we're going to do the plan, but it's going to go wrong. Yes, but we will go wrong with confidence. I mean, you know, and the point here is we have no process of determining the future before it happens. You can actually tell this. I mean, here's another one that I picked up. Okay? This is part of my Google search in 2020. You can tell this was done in 2018. Curiously enough, nobody predicted there would be a global pandemic in 2020 and that would disrupt every single piece of work that they and their clients were doing and force everybody to work at home. So yeah, it kind of messed up a few deadlines. Nobody predicted that because it's very difficult, especially about the future. Now, what I love about this quote, and this quote is kind of like humbling. I put Niels Bohr, question mark, because we don't know if it was him. There's lots of, you can go out on the internet, and there's lots of people who might have said it. Niels Bohr is my preferred one because I like the quantum weirdness of it. But we don't know, and this happened in the past. Somebody said this in the past, and we don't know who they were. If we can't predict the past, honestly, we're screwed for the future. So, yeah, there is a point, which also takes us to this observation. People often say this. I did say I talk about tools. You should use the right tool for the job. People say this so often. I know I've said it. I find it in books. I find it in posts. I find it in talks. I want you to pause for a moment and realize it's one of the hardest things you've ever told somebody to do. Because we don't know what the job is. We don't know what the right tool is, because we don't have total knowledge of all the tools, and we don't genuinely understand the nature of what we are building until we have built it. Apart from that, yeah, this is easy. But that's the problem. You don't truly know. As it unfolds, as the future unfolds, we have no way of going to the future and saying, guess what? Our tool choices, our library choices, our platform choices were wrong. This is what you should have done. And then passing that knowledge to the past. Physics currently tells us we can't do that. So, yeah, we have a bit of a problem there. And that problem actually manifests itself in other ways. Because people often talk about, we're going to prioritize things by business value. We're going to prioritize our features, our requirements by business value. The next piece of work is going to be prioritized by business value. There's a problem here. Physics tells us that this is actually not possible because you do not know the business value of something that you're working on until sometime in the future. So here's an interesting thing. You can estimate, you can prioritize by estimated business value, but you don't actually know the future. Yeah, the wisdom of Yoda applies at this point. So, it's another point here. A distributed system is knowable. And this is very easy to run into. Again, this is very easy to run into, particularly when you're focused on the world on your screen. This is the programming world as I see it, the source code as I see it. It works on my machine thing. You look through the world. You look at the world through the lens of your editor. And although you may be aware of a whole load of stuff that happens in distributed systems, sometimes you don't think about it from those points of view. You think about it from the code that you see rather than the context that it's in. So things we need to appreciate. So Martin Fowler messaged me this. Thought you ought to know that United may have discovered a kink in the time-space continuum over the Atlantic. The observation here being that the time to destination was 0, and he was halfway across the Atlantic. This is really not going to happen. The point here is the distance between Heathrow and Newark is 5,500 kilometers. That's not 19 centimeters. That's 19 light milliseconds. No, it isn't. It's a blank screen. That's all zeros. There it is. Oh, it's gone. 19 light milliseconds. That's the distance between basically London and New York. So therefore, if you have servers in London and servers in New York, and somebody gives you the requirement that these need to be in sync, replication needs to be in sync with respect to 10 milliseconds, you can't do it. Oh, you're not trying hard enough. No, really, you can't do it. Physics says, I can't do it. Take it up with Einstein. I know he's dead, but you're as likely to get through to Einstein as you are to get through a 10 millisecond sync. It's the point there is that you are dealing with a system that has separations. Indeed, every system has separations and latency. The processor is filled with stuff like this. This is one of the things that makes caching hard, is the fact that there is a displaced sense of time around a system. We are always dealing with distributed systems. Sometimes we're just very good at hiding it from ourselves. So in this book that I wrote, co-authored with Frank Bushman and Doug Schmidt, we gave a definition of distributed system. A distributed system is a computing system in which a number of components cooperate by communicating over a network. And that is a perfectly acceptable but very unexciting answer. Leslie Lamport's is always much better. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Yeah, that's more like it. And we find this kind of loss, we find this issue, this disruption of the illusion that we normally create. The idea is that software, when we create software, we are creating an illusion. And you get a choice in that illusion. You are telling a story. And that story is like, oh, my story involves objects and functions. My story involves these abstractions and these layers. You are choosing the story you want to tell. But you need to remember it's all an illusion. And it can come crashing down when it contacts reality. As is the case for one of my books. Somebody can't read your ebook in Pennsylvania. It's my publisher, O'Reilly. Well, this is awkward. Due to fires and power outages in California, it's unavailable. Due to problems with this device behind us, the screen is currently unavailable. But this is a point here. We have a perfect example of Lamport's law. Now, all of this ultimately boils down to Brewer's theorem, which is probably better known as the CAP theorem. He proposed it as a set of principles. Eric Brewer proposed it as a set of principles in the late 90s. But it was actually then later shown to actually be a theorem. CAP standing for consistency, availability, partition tolerance. So let's look at these first two, consistency and partition tolerance. The point is that you can choose any two, but not all three. That's what the CAP theorem is. Consistency. On a network, if we ask for data, let's ask for data at two different points, and we get the data value, we should have an agreement on that. If the two of us are sitting next to each other and we are using a social media application, for example, and I post an update and I can see that update and you do a refresh, you should see that update as well. You should see the same values, okay? Consistency, we see the same thing for correct values. Partition tolerance is the obscure term here. Partition tolerance basically means if your network becomes a not work, okay? If basically something breaks down, it partitions. Oh, we have one network, now we have, a router goes down, or something goes down somewhere. This basically says you either see the same thing or you see an error state. Okay? We will never show you a value that is inconsistent with what other people are being shown. But the application will still run. It won't crash. It won't go, oh, the network's down somewhere, or somewhere there's a fault, crash. It's just going to go, no, I can't give you the answer that you're looking for at this point. There is no answer. We've kind of seen that one. Then, there is no answer. The next one, you'll have to imagine it. For those of you online, you're already seeing it. The next one is availability and partition tolerance. We always get an answer, even when there's a problem. We tolerate failure. But what we do is we hold a cache. We hold on to a value. You get to see the older value. So in other words, there is always a value available, but that value might be stale, and it might not agree with what other people are seeing. Okay? No, still not back. Okay. And then the third option is the kind of curious option. You can have a value, and it is consistent, and it will always be correct, or we will crash in the presence of a network failure. That turns out to be less useful, and people normally go for one of the first two. But the idea is you can have any two of these. You cannot have all three. By the way, there are some very interesting implications of this for things like NFTs and cryptocurrencies in terms of bonds, but I'll leave that as outside scope for today. So the wisdom of Douglas Adams disappears from the screen even as I speak. But the wisdom of Douglas Adams, there's a lovely bit in the original Hitchhiker's book. We demand rigidly defined areas of doubt and uncertainty. The CAP theorem is effectively a way of saying there is just a limit to what you can simultaneously know. It's basically Heisenberg uncertainty principle for the distributed system. There is a limit to what you can know. You know more of one thing, or you get more of one quality, you lose more of another. So we can kind of return to Phil Carlton's observation. That's where we get the cache invalidation and naming things. We've done the naming things, cache invalidation. And you've probably experienced this one every now and then, haven't you? You're looking at the screen, and it says, hey, you have two of these things. And you're looking at a list of three things. I get this in a number of things. I've had it with Gmail, but I've also had it, Tumblr, pretty much anything. It's just like it tells you, you have n of these things, and there's either n minus 1 or n plus 1, but it's not n. And you're looking at this going like, how the hell did you screw up this badly? Because clearly there's a piece of code that has just iterated 3 times, and yet you're telling me this. And this is a real problem that we end up with, because obviously the answer is easy. This is a problem that you end up with fracturing micro front ends and things like that, where what you're doing is you're holding one piece of data that you got from one query source, and then you've got data from another query source, but you have not reconciled them. And the point is that reconciliation is, sometimes people say, oh, yeah, well, CAP theorem, eventual consistency, that's why you're showing this. And it's like, well, no, that doesn't make any sense. It's a feature of a distributed system that it may not be in a consistent state, but it is a bug for a client, for a single thing that can be made consistent to be inconsistent with itself. That's different. You have total control over the local stuff. If you have one process and it has 2 values and they disagree with each other, then you need to reconcile that, yeah? You need a way of breaking the tie on that one. So, the final thing, technical debt is quantifiable as financial debt. Now, this is an interesting one. Because this is an interesting one, because every now and then people say, oh, well, we've got this much technical debt, and they go and quote a value in euros. And it's just like, yeah, look, it's on our dashboard. This is how much technical debt we have in our code. Okay, let's understand the origin of this and then the resolution. An observation made by Meyer Lehman back in 1980, based on his work in the 1970s, so this is going back quite a way. As an evolving program is continually changed, its complexity, reflecting deteriorating structure, increases unless work is done to maintain or reduce it. This is way before the terminology that we now use to describe systems was there. But what I like is that he actually uses a term that we have somehow repurposed, well, not quite correctly. Maintenance. He's acknowledging that the very act of creating something will disturb the thing that is already there. And you will end up with collateral problems that are necessarily going to happen. If you decide to cook a meal, that means you will end up with dirty dishes. That's not a choice to not have dirty dishes. The choice is, what do you do with the dirty dishes? Your goal was not, what am I going to do this evening? I'm going to make some mess in the kitchen. Yeah, but are we going to eat? Yeah, maybe. The goal is, we are going to eat. I am going to cook something. It is inevitable that there's going to be that. And this happens when even if you are the most focused on the quality of your code as you are developing it, there will inevitably be some kind of collateral damage to your existing code because you are focused. The nature of human focus, and this is the dirty secret to a lot of these things, when you are focused on one thing, by definition, it means you are not focused on everything else. The concept of focus means you are ignoring. Good focus means really good ignoring. And you may have a number of ideas in mind, but there is a chance that if you've changed some abstractions and you've changed some concepts, they are outside the scope of your focus. And that's not a fault of you any more than it's a fault of being human. Because if you've got good focus, that you will inevitably have this. You then have to pull back and look at the kitchen and go, oh my goodness, who made this mess? Oh, wait a minute. Even when you're doing the right thing, you will discover things are not, you will only discover afterwards. It's inevitable. It's not a kind of an option. It's not laziness. It's an inevitability. The degree to which it happens, that's a separate question. But that is what we talk about when we talk about maintenance in the real world. Maintenance is to do with the physical interaction of doing stuff and physical wear and tear. If I have a washing machine, then the washing machine can break because it's physically used. We are physically involved with it. There is wear and tear. We need to maintain it. Code does not experience wear and tear of itself. You don't leave a piece of code for 10 years and then suddenly you come back to it 10 years later and it's like, oh man, look at this. The curly brackets are falling off, it's so old. The code does not age. You may feel like it's aged, but that's because you have changed. That's not the code, that's you. That's a relative thing. And that's quite a nice feeling. You should hopefully always look back. Occasionally you look back at your code like, wow, I must have been on fire that day. And it's just like, oh man, I'm causing a fire that day. It's more often the case. You're looking at something going like, oh, and guess what? Well done. You now know more than you did then. That's great. Because the knowledge that you're always working with incomplete knowledge. The knowledge that you need to do the thing you're doing today lies in the future. But you're still able to make progress. It just means that in future you will go, now I know what I should have done. Now I know what the right tool for that job is because I understand the tools in the job. But more importantly, with that code, we're saying you need to maintain it. It's not the code itself. It's our interaction with it. Now, that kind of matters because it's to do with the alignment of our metaphors. When we often talk about these things, we are talking about the language we use these days is often technical debt. I hear a lot of people say, oh, we have a technical debt problem. Now, I'm not going to say that people don't have a technical debt problem, but I am going to say in most cases it's not the problem. It's the effect. And we've confused the cause and the effect. Technical debt is often the effect, but the question you have to ask is, how did it get there? Oh, it just happened. No, it didn't just happen. The real problem is not that there is technical debt. Technical debt is fine. Somebody says, oh, we've got lots of technical debt. Yeah, but what's your problem? Well, we just said, Kevlin, we've got lots of technical debt. It's like, okay. Think about the debt metaphor. I've got a lot of debt. Okay, yeah, I prefer to have less debt. Is it managed or unmanaged debt? That's the whole point of the metaphor. Are we managing it? Oh, yeah, we've got a really solid restructuring approach to dealing with our debt. We restructure our debt. We're repaying it. Every sprint, we repay it. Oh, you don't have a problem with debt. Yeah? You've got debt, but you've clearly got it under control. You know, my wife and I had a mortgage. That's quite a big debt. But guess what? It was structured. It was structured over time. You knew exactly what was going to happen every month. We also had control over it. And in return, we got a house. Awesome. So there's a clear trade-off. There is not an intrinsic problem with debt. People have misunderstood. Debt is not a way of saying this is bad. The whole idea of debt was slightly different. The problem that most people are experiencing is neglect. We have the term neglect elsewhere, like physical neglect, emotional neglect. The idea is, and this is why neglect is hard to see, because it's a thing that doesn't happen. It's not a thing that happens, it's a thing that doesn't happen. You can't see a thing that doesn't happen. It's really hard to spot. Most systems struggle from the thing that does not happen. The way to look at it, and this kind of came to me when I was thinking about this with one company I visited twice, different periods of time. Well, actually 3 times, but there were 2 key visits. One, hey, we've got all this legacy code. We've got all these problems. We need to work out what to do with our legacy code. And so we came up with some ideas. And they applied them. And you know what? That kind of worked out. And then later, hey, we've got all this legacy code. It turns out they'd overlooked one thing, and so had I. The reason there is a boat on the screen in a moment, the reason there is a boat on the screen is you have to think, you're out in that boat, you're out in the water. There are holes in the boat. What are you going to do? The boat is sinking. Okay, this is fine. I can take the water out. You know what? You start taking the water out. Yeah, you haven't quite solved the problem. It turns out one of the things you have to do is stop the water coming in as well. And that's the bit we're not very good at. We're very good at saying, oh my goodness, let's get the water out. What do we do with all the unmanaged technical debt we've got? But not, how do we stop writing code that does that in the first place? How do we not create the situation that we find ourselves in? That's what's really going on. However, the question here that I want to explore is this actual specific aspect of the debt metaphor itself. It was introduced by Ward Cunningham. The debt metaphor was introduced by Ward Cunningham in 1992, but it was popularized. So some of us were using it in the 1990s, variously called technical debt, quality debt, design debt. There are a lot of terms. Martin Fowler helped popularize it about 20 years ago. Technical debt is a wonderful metaphor developed by Ward Cunningham to help us think about this problem. Like a financial debt, the technical debt incurs interest payments, which come in the form of the extra effort that we have to do in future development because of the quick and dirty design choice. But the key thing here is the word metaphor. It's a metaphor. It's like financial debt, but it is not the same as. People often then make this mistake. They make the mistake, as I tweeted, found myself again cautioning the category error of treating technical debt metaphor literally and numerically, converting the code quality into a currency value. You do not know what the financial debt of your code is. That is not possible. There are a number of reasons it is not possible, but this doesn't stop people doing it. It's a metaphor. Treat it like a metaphor. It's a way to give you language. Now, why is it that you can't do this? Now, sometimes people will say, well, no, we know the technical debt of our code. Look, we've got duplication. Yeah, but what is that duplication costing you? You know, come up with the euros and cents value. The problem is that some duplication is actually helpful because it introduces decoupling. If you look at a large system, some duplication is actually avoiding creating dependencies. That's a contextual trade-off. Do you know enough to be able to say, this one costs, this one doesn't? Here's a whole bunch of dead code. Well, sure, we should write it off, but the duplication in that code costs us nothing. In fact, nothing in that code costs us anything. I mean, we should delete it, but it's not worth the same as technical debt that might manifest itself in the main part of the program. So the point is, the tools that do this do it naively and incorrectly. But then occasionally I get the idea that sometimes people say, oh, well, no, technical debt. We know the technical debt in our code. We've estimated, not in money, we've estimated in hours. We've gone through as a team and worked out how long it would take us to fix the technical debt, to repay the technical debt. Okay, that's reasonable. But that is an estimate of the work required to repay the debt, but technical debt does not equal the cost of repaying the debt. That's a misunderstanding of the metaphor. The whole point of the metaphor is the disappearance on the screen, is that technical debt is the cost of owning the debt. That's not the same as today's repayment. So the idea here, the message of the technical debt metaphor, it is not simply a measure of the specific work needed to repay the debt. It is all the additional time and effort added to all the past work, the current work, and the work in future from having the debt in the first place. And if you remember, we can't predict the future. You don't know what this is going to cost you. You can work out how much effort it will take. You can estimate that. But that's not the same as the cost of the debt. That was the point of the debt metaphor in the first place, to allow you to reason about it. It's actually a complex financial instrument. So, we reach a conclusion, and we reach lunchtime. And instead of having time at the end, I've ended up with time in the middle. But I'm happy to take a couple of questions if the lunch, But I'd just like to leave us with Aldous Huxley's observation: reality cannot be ignored except at a price. So thank you very much. So you can escape if you want to, but we will take a couple of questions now. Take one for one.
There should be lunch outside, probably upstairs, maybe downstairs.
This sounds very probabilistic. There's a rigidly defined sense of uncertainty in that here.
Unknown, as we learned today. I just ask an online question now. What are the tools or language features to handle NaN?
Is NaN. I mean, really, that one is, it's one of those things. It's well defined where it occurs. It's really a question of awareness. And don't just rely on yourself, rely on other people, rely on other tools, as in static analysis if they're able to detect it. But mostly the tools you're relying on is your colleagues and your own awareness. Use checklists. When you are testing for things, if you are using floating point numbers, always ask the question, what happens if I give this a NaN? Okay? The one question I didn't answer with arithmetic mean is what happens if the input data has a NaN? I carefully removed that from the talk because it's a much bigger question. But the idea there is the tool you're mostly relying on is this and other people. And anything else a static analysis tool will give you, but mostly it is the awareness. Am I using floating point numbers? Am I casually treating floating point numbers as if they were just integers or real numbers? And if you can see that, then it's like, okay, here we need to check this. But there's nothing magical I can offer beyond that.
What are your thoughts on do things the first time practice? Do things right the first time practice in software development versus have trade-off between quality and focus on getting features out fast? Can quality and fast delivery go together?
Okay, yeah. So this is a question that has a very big answer. So I'll try and give a very small answer to it, but with the acknowledging that it's incomplete. The idea of do something right the first time. The probability that will happen is quite low. And the problem is that sometimes what we do it can end up we're working with a limited pool of knowledge. In other words, we start thinking, I am doing it right. But what we're doing is actually closing down. We're focusing on something here and not looking at a bigger picture. So what we end up doing is missing certain things. So my general advice is do something as well as you can the first time. It may not be right, but here's the trick. Play with an open hand. What do I mean by that? Card games vary in their format. There's lots of different kinds of card games. Many card games are closed hand. You can't see what everybody else has got. Some are open hand or partially open hand. You can see something else on the table. You can see what's going on. The idea is you want to play code with an open hand. Think about your conventions. Communicate what you're thinking as much as possible in your names, in your structuring. Any supporting documentation you offer, things like ADRs and things like that, in your test. Don't make your test just test for correctness. Make your test express what you're thinking. It doesn't mean that what you're thinking is correct, but you're playing with an open hand. Somebody can come along later and go, I think you've made an incorrect assumption here. That someone might be you. It might be in 1 hour. But the idea is if you play with an open hand, what you're doing is you're offering people, here's what I was thinking. Your thinking might not be right, but you're showing what you were thinking. And it's much easier for somebody to then come in and go, yeah, we can adjust this and we can converge on what is right. So my thinking on the whole process idea is play with an open hand, be wary of perfectionism. Perfectionism is a dysfunction. It is actually a behavioral dysfunction. There's a psychological aspect to perfectionism, and we often fall into it without realizing it. But that doesn't mean, you know what, I know this is a really bad practice, but I'm going to do it anyway. No, it's I am working at the level that I can currently work at, but I'm going to show you what I'm thinking, because I might be missing something. Yeah, and that's the idea. Play with an open hand and be as open with it as possible, but iterate, allow convergence.
Yeah.
And a real question from a real human being. I'm not saying that all you people online are not real. I just don't know, okay? I mean, you could be dogs, you know, and I've got nothing against dogs. Well done. We'll pause for effect. Okay.
So we are not measuring engagement, but
no.
Only a few counts. Continuing with the discussion about we cannot know the future, so we have to estimate all our projects, and we should estimate like what we expect now, multiply it by 3, and assuming we get it the first time right with the estimation, so we succeed, then we have to write it again, and from learning the second time, we can write it for the third time, and now it's actually a good program, isn't it?
Kind of. The thing is, what you get, so the thing is that we have a metaphor that we often use without realizing it. We use a manufacturing metaphor in code. And it turns out the compilers are great at this metaphor. Build pipelines are great at this metaphor. We are not very good at this metaphor. When we are doing something, most of the time, the reason we are writing some code is because that code does not exist. That means that we're doing something new. Now, the degree of newness varies. It's either new to me, or it's new to the world. You might be writing functionality that does not exist in the product or any product yet. So there's a whole ratio in which it is new. Now, what does that mean in practice? It means that it's not necessarily repeatable, which means that we've got to be very cautious about our ability to get better at our estimates. Because sometimes we do get better at mostly acknowledging, this one feels familiar. I see this problem. There's enough familiarity that I can converge on this one. This, however, is a big unknown. I cannot estimate it with the same variance. It's got a much larger variance. I genuinely don't know, because I've not done anything like this before. We as a team have not done anything like this before. We as a company have not done anything like this before. We are using a new technology stack. We are dealing with a new product domain. The more new something is, the less likely it is that your estimates are going to be able to converge with any kind of meaning. But the problem is, because most software is about creating something that doesn't already exist, you will always be dealing with some degree of variance. So the trick is really look at the things that become more determined, but also be very careful to distinguish them and not mix them. This is the biggest problem with estimates and adding estimates together. In the world of estimates, 2 + 2 = 5. Because when I say that this takes 2 days and this takes 2 days, what I'm saying is that this is 2 plus or minus some amount. And this is 2 plus or minus perhaps a larger amount. 2 + 2 does not equal, there's a skew in the distribution. It ends up being 5 plus or minus. And so that's the issue. So the real trick is to learn to distinguish between the things which are familiar and the things which are not, and don't mix them by adding in a simple way. Yeah. So we can get some convergence. We can get better at it, but it might vary.
And it's never perfect.
And of course, it's never perfect. The knowledge that you need is in the future. But as human beings, human beings have this wonderful ability. We work with incomplete knowledge. We are great at it. We get up every morning. We have no idea what's going to happen that day. And maybe we have some idea, but the chances are it turns out. I mean, if you knew what the next talk was going to involve, you wouldn't bother going to it because you already know it. The reason you're going to it is because you don't know it. And that may inspire a conversation that leads you to somewhere else and leads you to have a different conversation afterwards. And perhaps you don't go to the talk after, or you go to a different talk. You can, but that's fine, because you're human, and your superpower is being able to work with incomplete knowledge. The problem arises when you fool yourself that you have complete knowledge. Yeah, that's the problem. If you wake up and go, I know exactly what's going to happen. I've got a plan for this and this is my day. And nothing is going to change that. At that point, your roadmap is set to fail. Okay, and on that kind of big note, it's lunch. Thank you.